So I already mentioned Taylor columns as something that will come out of these balances. So let's see formally how actually it comes about. So Taylor-Proudman theorem emerges directly out of this geostrophic balance we started with and the non-divergence in the horizontal plane. So starting with our geostrophic balance equations, which you should get very familiar with, minus 1 over f rho dp dy and 1 over f rho dp dx. We will use a incompressible fluid and assume rho is a constant, not a function of pressure, and f is also constant for this particular derivation. Actually, if you think about the sphere, we said there is f varying from 0 to the pole. F is 0 on the equator and keeps increasing to the pole. And we had a beta effect which was df dy, the variability of f in the meridional direction, the gradient. And most of the time, if you take a region that's small enough, let's say synoptic scales, then variation in f is actually quite small. So the so-called f-plane assumption gets made, or beta plane assumption gets made, where f is not constant but it's some f0 plus beta y. It's linearized around some f in the middle of the study area and so on. So we won't go into the details, but in this particular case, assuming f and rho to be constant, we get obviously a very simple situation. We can take the z derivative of these, so dug dz will be minus 1 over f rho dp dy dz, and dvg dz will be 1 over f rho dp dz dx. Obviously, what are we doing? As soon as you hear dp dz, hydrostatic balance should come to mind. So the geostrophic flow, we can use dp dz dy and dp dz dx with hydrostatic balance and get the gradient in this coordinate dug dz dvg dz to be 0. Okay, so how do we do that? You replace dp dz here with minus rho g and dp dz here with minus rho g, and rho is constant, g is constant, so obviously they don't have gradients in x and y. Remember, rho is already constant and f is constant. So you end up with dug dz and dvg dy both being equal to 0. Okay, I hope I said it right. Both are equal to 0. So neither u nor v is varying in the z direction when f and rho are constant. Going back to our full equation then, du dt plus 1 over rho grad p plus grad phi equals minus 2 omega cross u plus f. I say this all the time so that you kind of hear it again and again and see it again and again, so that you get comfortable with it. So we are still in the Rossby wave being small domain, so geostrophic balance is valid, and we are going to ignore friction again. So imagine that we are away from the surface. So we are going to end up with, take 2 omega u cross u over here, 2 omega cross u plus 1 over rho grad p plus grad phi equal to 0. Since Rossby number is small, we drop this term, and we said friction is not there. So this is what will be the result. Why? Because if the flow is not varying in the z direction, we will see that the fluid becomes stiff in the direction parallel to rotation. That's easier to imagine in a rotating tank, right? Where the rotation axis and the z-axis are in the same direction. So going to this equation again with Rossby number small and f equals 0, and remembering phi is gz minus omega squared a squared cosine squared phi divided by 2, where this is our centrifugal force. So we have absorbed the centrifugal force by writing it as a gradient, and along with gravitational constant. Remember the modified gravity or measured gravity and all those good things. So we had for geostrophic flow Fz cross U plus 1 over grad P equal to 0. So we wrote Ug and Vg in that case as these equations, which we have already seen multiple times. And we can write now the vertical component of this equation as the hydrostatic balance, right? We are still holding on to this because there is no reason to give it up yet. So you take a gradient cross of this equation, and I will show probably some vector calculus associated with that. So cross product of this equation with gradient operator, and if rho is only a function of pressure, now we are adding a slight complication. Rho is not just constant in every direction. It's constant in the horizontal direction because it's only a function of pressure, and pressure is varying, let's say, only in the z direction in the water tank, but we will go to the real world later on. So in that case, this equation basically becomes, you can go through the calculus and show that omega dot grad u equals 0. This is the same equation we wrote before, where we said dug dz and dvg dz were 0. So these are the two main vector identities we need. Grad cross grad phi becomes 0 because grad cross grad of a scalar is 0, and we need grad cross a cross b equal to a grad dot b minus b grad dot a plus b dot grad a minus a dot grad b. That's kind of long, but you don't, if you remember, great, but you can derive it by going through the matrix, or you can always refer to it from this table. Okay, but the main thing is when we do the grad cross grad of 2 omega cross u, we are going to end up with 2 omega grad dot u minus u grad dot 2 omega plus u dot grad 2 omega. We applied this exact identity here. Okay, minus 2 omega dot grad u. So each of these terms is given here, and you can begin to see which term will begin to go to 0. So going back to our equation of f equals 0 and du dt 0, we take the grad cross, and do one term at a time. So grad curl of this term is minus 1 over rho squared grad rho. So if you do grad curl of this, you will get minus 1 over rho squared grad rho cross grad p equal to 1 over rho squared. You can take, right, you can switch these. That's another vector identity. Here it's grad rho cross grad p. You can just switch it, and that makes this negative sign disappear. So you have 1 over rho squared grad p cross grad rho. That's all. We're just manipulating these things a little bit. So we can then equate the, so this obviously went to 0 because grad cross grad phi is 0. We are just balancing these two terms. This became 2 omega dot grad u, okay, because here these terms go to 0. All these terms go to 0, so you get 2 omega dot grad u equal to 1 over rho squared grad p cross grad rho. What is this grad p cross grad rho? Remember that rho is only a function of pressure. So that means the density surfaces and pressure surfaces are parallel to each other, which means their cross product will be gradient of their cross product of their gradients will be 0. Okay, the fluid that is got a density that's only a function of pressure is called a barotropic fluid. Okay, this term will come up again later on, so just remember the simple manipulation we did, and we will see that this vector grad p cross grad rho is going to be our baroclinicity vector, and that term will give us this special Taylor-Proudman theorem that we are trying to derive. I cut it off there because I didn't want to put too many derivations in one podcast, but you can watch this again and make sure you followed each step, including the vector identities that we used to get there, and the assumption that rho equals rho p, so it's only a function of pressure.